Um, Hi, we are going to talk about high voltage DC. I'm Sebastian Rodriguez and my partner Jesus Sepulveda. What does HVDC means? High voltage direct current. The primary object of an HVDC grid is to transmit power amongst its converter situations, just like an AC grid, but it has its own advantage. The HVDC system are the moving from stage of point to point (PTP) connectors to the stage of the transmission system, interconnecting more than two stations and utilizing multi-terminal (MT) multi-vendor HV voltage source converter systems. And an image to explain the line. It started with winds power that it's it used as a transmission line to come to converter station, then HVDC transmission line and inverter station, then HV transmission line again, and finally the distribution line in the town.
So when we have HVDC for renewable energy, we usually as it in PDP. When it happens, we are talking about offshore wind power plants, which means that wind power production is subject to wind conditions, which implies that long and expensive PTP connectors are only fully used during relatively short periods. Non-PTP topology reduces the number of VSC stations, which also reduces the asset cost and maintenance. So that's what we have when we have PTP and non-PTP. So now we have to talk about the grid controller. The grid controller is a high-level controller linked to each individual VSC station. Its main purpose is to provide the VSC station controller with their control characteristics and reference value. So we have the grid controller for many VSC. So we have four VSC stations A, B, C, and D. So we have set points that the controller makes sure keep under reference. It also makes sure that dominant frequencies existing in the HVDC grid shall be identified. We need to know what they are via simulations or Fourier measurements. So we have harmonic voltage, even if we have DC-DC, and we have some harmonic impedance also in our circuit. We need to specify because we need to avoid them. We need to avoid the critical resonance frequency in any operation point, in any set point of the grid. So when we have HVDC, we need converters, just like this or like that. And these converters usually needs device, just like that one we have here, to make sure we can operate.
We start with device evolution. Ignitrons, an image of ignitrons. On last century, before the use of semiconductors in power electronics, mercury rectifiers were one of the few methods to rectify the current that arrived from the distribution network. That's it, to go from alternative current to direct current. So the we can see that it's like a stone, like a like a LED. It would be. And the parts: anode, cathode, ignitor, mercury, ceramic insulator, and cold fluid. Um, the mercury is too much toxic, so I guess it was the reason why stop using ignitrons to rectify the current.
So we have now the restores. Restores are based on that power switches should ideally be on or off with as short a transition period as possible. That means they need to be fast. This leads us to these devices, the restores, that are solid-state semiconductors conducting only when the gate receives a current trigger and continuing to conduct until the voltage across the device is erased. So it's just like a trigger diode. We have it there. We can model it like the transistors, but that's basically the PN-PN junction that make it work just like that. So when we trigger it, we rectify the wave. So we can select how many times on the wave we need to have for the power conversion. Similar device is transistor. They are used to amplify or switch electrical signals in power, so we can use them with a small signal in the base, and between the collector and the emitter, we let through a current. We will drive a high current, and that's usually called a beta gain. So this is useful for some device, also used in power electronics, just like optocouples, that just like kind of protection devices. Just like any other power switch, we can see how it works. Even if we don't have that PCC main bulbs common there, we can have some other small voltage power source with common ground there, and we can still keep switching the LED without any problem thanks to the transistor. So thanks to that, we can have converters. That's what we use for HVDC and power electronics. In DC-DC, we have that step up that's regulated in some operation frequency, that's 1 kilohertz in this case. So we have the circuit input voltage, 5 volts, and we have one Henry inductor here. We have a freewheeling diode, a transistor, a capacitor, and the load resistance. That might be any other thing, just like a motor, but in this case, it's a resistive load. So we are talking about a gain that's likely most bigger than 1. We have a big gain when D comes to 0. But we don't want D to be 0. D is the duty cycle. So when we have the duty cycle here, we operate the circuit, we change the polarity of the diode, so current takes on that path, which means we can actually be regulating the current depending of an operation point.
Um, we the next circuit is a chopper converter. It consists on two steps. In the first position, the switch is connected and the coil is filled with energy, and that energy charge the capacitor. Then the load, the resistive load, is charged with the voltage in the capacitor. For the second position, the switch opens and the energy that contains the coil flow through the resistive load, and it continue to to the voltage in the capacitor. So about if the switch is open, it doesn't matter to cut the energy. So the energy it cuts, but the load resistive have power then. So uh, the capacitor continue discharge his energy of the load, and the chopper consists on that. The step first and second switch too fast, then the coil is charging and discharging all the time, and the capacitor is the same thing. So the voltage it maintains in the same value. In,
So, in order to that circuits work, we need a PID control device that ensures that switching leads to the reference voltage. So we have some error amplifier, the PID controller, a comparator that's a sawtooth waveform allows the comparator to create a PWM signal. So we can drive the circuit to DC-DC converter according what we need. We need boost to step down. So we make sure we have this clear and we can buy a controller to our circuit. So that's all. That are papers and reference used for this video. Uh, Technical guidelines and prestandardization work for first HVDC grids, and, and criterion for the electrical resonance stability of offshore wind power plants. And we also consult winderror.org.